Hey everyone, this video is on Lewis dot diagram. The Lewis dot diagram, or Lewis dot structure, offers a representation of a molecule structure. This includes showcasing the number of bonds and the specific electron arrangement around atoms in the molecule. Here you can see the Lewis dot structure for water, where the oxygen atom is connected to the adjacent hydrogen atoms via two covalent bonds, and also the oxygen atom has two pairs of lone electrons that do not participate in any bonding. So therefore, the Lewis dot structure helps us understand how atoms are able to connect together to form a molecule and helps us visualize what the molecule actually looks like. There are a number of steps that are involved when you're drawing the Lewis dot structure. The first step is the most important, that is to determine the total number of valence electrons each atom has and all together in the molecule. Once you have determined the total number of valence electrons, you will then need to draw a hypothetical structure by connecting the atoms via single bonds and placing the least electronegative atom in the center of the molecule. The exception for this rule is hydrogen. Hydrogen atoms, because it only has one electron in its outermost shell, it cannot be the central atom. After drawing the hypothetical structure, we need to always consider the octet rule, that is, whether the atoms have completed the outermost shell. Remember that atoms only participate in bonding and come together to form compounds and molecules to achieve a complete and stable electron configuration, and that is known as the octet rule. And the fourth step, which I will discuss in more detail when we get to it, is to calculate and minimize what we call formal charges on the atoms in the molecule. The first step to drawing Lewis dot diagram is to calculate the number of valence electrons of each atom in the molecule. This is done by familiarizing yourself with the periodic table. Remember, the periodic table is divided into columns, which is referred to as groups. The first column is called group 1, group 2, and the transition metals will go from group 3 all the way to group 12, and this is followed by group 13 all the way up to group 18. Elements in group 1 and 2 will have 1 and 2 valence electrons respectively. Elements in group 13 will have 3 valence electrons. Elements in group 14 will have 4 valence electrons, and this is followed by the same pattern of 5 valence electrons in group 15, 6 valence electrons in group 16, 7 electrons in group 17, and finally, noble gases, which are the elements in group 18, have 8 electrons. They have already fulfilled their outermost shell. So when you're drawing Lewis dot structure, have your periodic table ready, as you will need it to determine the valence electrons of each atom in the molecule. Let's begin by using the simple example of water. Water consists of 2 hydrogen atoms and 1 oxygen atom. So the total number of valence electrons is 2 times by 1, which is the hydrogen atoms, by 6, which is the valence electron in the oxygen atom. And this gives you a total number of valence electron of 8. We'll then need to draw the hypothetical structure by placing the least electronegative atom in the center. Now in this instance, although oxygen is more electronegative than hydrogen, the oxygen atom is actually the central atom because hydrogen atoms can never be the central atom due to its lone electron. So we'll place the oxygen atom in the middle, surrounded by its 6 valence electrons, and neighboring the oxygen atom we have the 2 hydrogen atoms, each has its own 1 valence electron. We'll then use 2 electrons, one from each of the neighboring atoms, to create a covalent bond between the oxygen and hydrogen atom. So we'll take 1 electron from the hydrogen and 1 electron from the oxygen to form 1 bond, and we'll do the same thing with the other hydrogen atom, and this is what we'll get. Because the oxygen atom has used 2 of its electrons to form the 2 covalent bonds, we'll have 4 electrons remaining, and the 4 electrons will be present as 2 pairs of non-bonding electrons. This is my hypothetical structure for water. After drawing the hypothetical structure, we need to consider the octet rule. We need to consider whether every atom in this molecule has fully completed its outermost shell. So for hydrogen, it has 2 electrons in this covalent bond, and because the first shell has a maximum number of 2 electrons, the 2 hydrogen atoms have achieved the octet rule. What about for oxygen? Well, oxygen, it has 4 non-bonding electrons and 4 bonding electrons in the 2 covalent bonds. So this adds up to 8, which again helps oxygen complete its octet rule, or the outermost shell. The last step, once the octet rule has been satisfied, is to calculate and minimize formal charges. Formal charges refer to whether the atom in the molecule has a positive or negative charge. The way we calculate this is by taking the number of valence electrons the atom has minus the number of non-bonding or lone electron pairs that the atom has after forming bonds, and then minus the number of bonds that it has formed. In the hypothetical structure of water, the oxygen atom starts with 6 valence electrons and will minus the number of non-bonding electrons, which would be 4, the 2 pairs of electrons in the lone pairs, so minus 4. And the oxygen atom also has 2 bonds, so minus 2. And this gives a final answer of 0. So the oxygen here has a formal charge of 0. We can also do the same for the 2 hydrogen atoms. Hydrogen has a valence electron of 1 and will minus the non-bonding electrons. But the hydrogen atoms don't have any non-bonding electrons, so minus 0. And for each hydrogen atom, it has 1 single bond, so minus 1. So again, we arrive at a formal charge of 0. This is the ideal case for molecules, when the atoms have a formal charge of 0. So when this is the case, there's nothing more you can do. Since this structure for water has already satisfied the octet rule, and the formal charges of all the atoms are already minimized, that is equal to 0, this is the correct Lewis dot structure for water. Now, when we are minimizing formal charges, this is done by moving electrons between lone pairs and bonds. And we'll look at this in further examples that actually require us to minimize formal charges. Whatever the charges will become, remember that the overall charge of the molecule must stay unchanged. So for neutral molecules where the overall charge is 0, no matter what the charges of the individual atoms are, they must always add up to 0. Now, inevitably, sometimes an atom in the molecule must be charged. Either it can have a positive charge or a negative charge. Let's go through a second example, which is carbon dioxide. Carbon dioxide consists of 1 carbon atom and 2 oxygen atoms. The first step is to calculate the total number of valence electrons using our periodic table. So oxygen has 6 valence electrons, so we'll do 2 times by 6. And carbon is in group 14, so we'll plus 4 as its valence electron. This gives me a total of 16. And we'll draw the least electronegative atom, which is the carbon, in the center, next to the 2 oxygen atoms. The next step is to draw a hypothetical structure by connecting the carbon atom via single bonds to the oxygen atom. Now, you can choose to do this by using any 2 electrons to form a single bond. In this case, I'll use the 2 pairs of electrons from carbon to form the 2 covalent bonds that's required. And this is the hypothetical structure I will get. The next step is to consider the octet rule. Does every atom have a fully occupied outermost shell? For oxygen atom, we've got 3 pairs of non-bonding electron, which add up to 6, and 1 pair in the bond. So for both oxygen atom, we have 8 valence electrons. However, for carbon atom, it doesn't have any non-bonding electrons. It only has the 2 pairs of bonding electrons, which add up to 4. So carbon atom here, unfortunately, has not yet achieved its octet. So what do we do? Well, a solution to this is to move another pair of electron to form a second bond between the carbon and oxygen atoms. And by doing so, we have a molecule whereby the carbon atom has a double bond to the 2 oxygen atoms. Let's try again. Does this molecule satisfy the octet rule? Well, for oxygen, we've got 2 pairs of non-bonding electrons and 2 pairs of bonding electrons, which add up to 8, so 8 for both oxygens. And now for carbon atom, it has 4 bonds, each containing 2 electrons. So we've got 2, 4, 6, and 8. So the carbon atom also has achieved the octet rule. And finally, the last step is to calculate the formal charges, and if any charges, we need to minimize them. Remember, the formal charge is calculated by taking the number of valence electrons minus the number of non-bonding electrons and minus the number of bonds. So for oxygen, we have 6 valence electrons minus the 4 non-bonding electrons minus the 2 bonds. And this gives me 0. And this is what we want, a 0 formal charge. What about for carbon? Carbon has 4 valence electrons minus 0 non-bonding electrons minus 4 bonds. So again, we get to a formal charge of 0. So because all the atoms in this molecule of carbon dioxide have already achieved a formal charge of 0, this is the correct Lewis dot structure for carbon dioxide. Example 3, sulfur trioxide. Sulfur trioxide consists of 1 sulfur atom and 3 oxygens. The total number of valence electrons is equal to 1 sulfur times by 6 because it's in group 16, and 3 oxygen atoms times by 6 as well, because oxygen is also in group 16. And this gives me a total of 24 valence electrons. Remember, we need to place the least electronegative atom, which is sulfur, in the center, surrounded by the oxygen atoms. The next step is to draw a hypothetical structure by connecting the sulfur atom via single bonds to the surrounding oxygens. Now, we can do this by moving the 3 pairs of non-bonding electrons of sulfur to form these 3 covalent bonds, and we'll arrive at our hypothetical structure. The next part is to consider the octet rule. Does every atom have a fully occupied outermost shell? The 3 oxygen atoms have achieved an octet because it has 3 pairs of non-bonding electrons, which add up to 6, and 1 pair of bonding electron in the covalent bond, which add up to 8. What about the sulfur? The sulfur has no bonding electrons, but it has 3 bonds, each containing 2 electrons. So unfortunately, sulfur only has 6 electrons in total. It's missing 2 more. So what do we do here? Well, a solution to this is to use one of the oxygen atoms and its lone pairs and move this to form a second bond between the sulfur and oxygen. And this is what we'll arrive at. Now, the sulfur atom has 4 bonds, which add up to 8 total electrons. The oxygen that has donated its pair of electron still maintains its octet because it's got 2 pairs of non-bonding electrons, so that's 4, and 2 bonds. Again, add up to 8. Is this the correct Lewis dot structure though? Remember, the last step is to calculate the formal charges and minimize them. As it's already being shown on the screen, sulfur has a formal charge of +2 because it has 6 valence electrons, it's got 0 non-bonding electrons, and it's got 4 bonds. And this adds up to the total formal charge of +2. For the oxygen atoms with a single bond, we have 6 valence electrons, minus 6 non-bonding electrons, and minus the 1 bond. It forms the sulfur. This gives a formal charge of -1. And this goes the same for the other oxygen as well. So how do we minimize the formal charges? Sulfur and some elements in period 3 and beyond have a property called expanded octet, where the atom can actually contain more than 8 electrons in its outermost shell. In this case, the sulfur atom can actually take up to 12 electrons. This property is very useful because then we can use the 2 negative charged oxygen atoms to further form bonds with the sulfur atom. By doing so, the sulfur atom now will have a formal charge of 0, so 6 valence electrons, minus 0 non-bonding electrons, minus 6 bonds gives us a formal charge of 0. And the oxygen atoms will start with 6 valence electrons, minus the 4 non-bonding electrons, minus 2 bonds, will also have a formal charge of 0. If you count the number of electrons on sulfur, we've got 6 bonds, each containing 2 electrons, so there are a total of 12 electrons. Not every element can have an expanded octet like sulfur. Only some elements in period 3 and beyond can have this property. Let's draw the Lewis dot diagram for nitrogen oxide. Nitrogen oxide consists of a nitrogen atom and an oxygen atom. The total number of valence electrons will be 5 coming from the nitrogen and 6 coming from the oxygen, which gives us a total of 11. Because there are only 2 atoms in this molecule, we don't need to consider which one is the central atom. But for the sake of revision, nitrogen is less electronegative than oxygen. So we'll draw the 2 atoms surrounded by their valence electrons. The next step is to draw a hypothetical structure by using one of the electron lone pairs to form a bond. Let's use the electron lone pair from nitrogen to form a covalent bond between the 2 atoms. You can also draw the structure by using a lone pair from oxygen. It will work either way. So by using the electron from the nitrogen atom, this is what the hypothetical structure will look like. The next step is to consider the octet rule for every atom. For nitrogen, we have 3 non-bonding electrons and 2 electrons that are in a bond. This gives us a total electron of 5, which means the nitrogen atom has not yet reached octet rule. The oxygen atom, on the other hand, has 6 non-bonding electrons and again 2 in the covalent bond. So it has achieved the octet rule. So how do we help the nitrogen achieve a fully occupied outermost shell? Well, we can use another lone pair of electron from the oxygen to form a second bond between the 2 atoms. By doing so, we'll achieve a structure whereby the nitrogen has 3 non-bonding electrons and 4 in the 2 covalent bonds. This gives a total of 7 for the nitrogen. For the oxygen, the number of valence electrons it has still remains 8. Now we're getting close to a fully occupied outermost shell for the nitrogen, so we can try donating another pair of electrons from the oxygen to form a third bond between the nitrogen and oxygen. Now this is actually going to increase the number of electrons for nitrogen from 7 to 9. We have skipped over 8. This brings me to the point. For some elements, particularly in situations where the total number of electrons in a molecule is an odd number, sometimes you will never be able to achieve the octet rule. In this instance, nitrogen can have either 7 electrons or 9 electrons. In these cases, you can skip the octet rule step and move on to the final step of calculating and minimizing the formal charges of the atoms in the molecule. So when the nitrogen has a single bond with oxygen, it has a formal charge of +1. Because it starts with 5 valence electron, it will subtract 3 non-bonding electrons, subtract 1 bond, which gives us a formal charge of +1. For the oxygen, we start with 6 valence electrons minus 6 non-bonding electrons minus 1 bond, gives a -1 charge. By forming a second bond between the two atoms, the formal charge of the two elements becomes 0. For nitrogen, 5 valence electrons minus 3 non-bonding electrons minus 2 bonds gives 0. And for the oxygen, we started with 6 valence electrons minus 4 non-bonding electrons minus 2 bonds gives 0 as well. So between the two structures here, although neither of them satisfies the octet rule, we would go with the structure that has the lowest charges for each atom. This is the correct Lewis dot diagram for nitrogen oxide. So far, the examples we've gone through all involve molecules that have an overall charge of 0, so they are neutral. For polyatomic ions, or any molecules that have an overall charge of non-zero, we need to add and subtract electrons depending on the charge of the ion in the very first step. If a molecule has an overall charge of -1, we need to add an additional electron to the total electrons that we calculated in step 1. If a molecule has an overall charge of +1, we need to subtract an electron from the total. And for the Lewis dot diagram for these polyatomic ions, or molecules with charge, we need to always include the overall charge outside the bracket around the structure. I'll show you what this means in a moment. Some examples of polyatomic ions you'll come across will be hydroxide, which has an overall charge of -1. So here we'll need to add 1 electron. Sulfate, which has an overall charge of 2-, which means we need to add 2 electrons in the beginning. Nitrates, we also add 1 electron. Ammonium, which is a cation, has an overall charge of +1. So here we actually need to subtract 1 electron from the total in the beginning. Let's go through an example for polyatomic ion hydroxide. Hydroxide has a molecular formula of OH-. So typically we'll start by drawing the valence electrons for oxygen and hydrogen. Oxygen has 6 valence electrons and hydrogen has 1. But because for this ion there's an overall charge of 1-, we need to add 1 extra electron to either the oxygen or hydrogen before we draw the hypothetical structure. So now we can draw the hypothetical structure by connecting the two atoms with a bond. We can use the 1 electron from the hydrogen and the extra electron from the oxygen that we just drew in, and this gives us this particular structure. The next step is to confirm whether the atoms have satisfied the octet rule. For oxygen, we've got 3 pairs of non-bonding electrons, which add up to 6, and 2 electrons in the bond, so it has 8. Hydrogen, because it only has 1 shell, it has 2 bonding electrons, which gives a total of 2. So both atoms in this case have fulfilled the octet. The next step is to calculate and minimize the formal charges. For oxygen, the formal charge will be 6 valence electrons minus 6 non-bonding electrons minus 1 bond, which gives a charge of -1. And for hydrogen, we started with 1 electron minus 0 non-bonding electrons minus 1 bond, which gives a formal charge of 0. In this instance, because the overall charge of the molecule of hydroxide is -1, we should leave the formal charge of oxygen as it is. Now remember, for polyatomic ions, we should always write the overall charge for the molecule in the top right corner outside the bracket as shown here. So we'll move the -1 charge from the oxygen outside the bracket to indicate that this charge applies to the whole molecule. The Lewis dot structure or diagram for ionic compounds works a bit differently to covalent molecules that we just discussed. it's actually a bit more simple. In ionic compounds, it usually consists of metal atoms that tend to lose electrons and become cations in the process, which are positively charged. Non-metal atoms in ionic compounds will gain electrons and therefore become negatively charged and are called anions. So when you're drawing the Lewis dot diagram for ionic compounds, there are only two things we need to do. We need to show the charge of each ion after they have lost or gained electrons, as well as the ratio between the ions in the compound. And this is usually indicated in the empirical formula for the ionic compound already. So let's go through an example. Sodium chloride. Now sodium is in group 1, so it has a 1 valence electron. Chlorine is in group 17, it's one of the halogens, it has 7 valence electrons. The ionic compound between them is simple. Sodium will lose 1 electron to the chlorine, and therefore the ratio between them is 1 to 1. When sodium loses an electron, it becomes sodium plus, and when chlorine gains an electron, it becomes chlorine minus or chloride minus. When you're drawing the Lewis dot diagram, remember we have to show the electron arrangement. Sodium has lost the 1 valence electron, so therefore its original shell is now empty. Chlorine atom, on the other hand, has gained that 1 electron from sodium, and it has a fully occupied outermost shell. Because the ratio between the two ions is 1 to 1, we don't need to indicate any ratio in front of the ions. The empirical formula for magnesium fluoride is MgF2. This is because magnesium is in group 2, indicating it has 2 valence electrons. Fluorine is a halogen, also in group 17, so it has 7 valence electrons. To complete the octet, magnesium has to lose 2 electrons, and each of the electrons will be given to each of the 2 fluorine atoms for the fluorine to complete its octet. When the magnesium loses the 2 electrons, it becomes magnesium ion with a charge of 2+, and when the fluorine atom gains 1 electron, it becomes the fluoride anion with a charge of minus. Like before in sodium chloride, the electron configuration or arrangement for the magnesium ion is empty because it's lost the 2 electrons. And the electron configuration for the fluorine ion will be a fully occupied outermost shell with 8 electrons. In this case, the empirical formula of NgF2 must also be reflected as the numbers in front of the 2 ions. 1 magnesium ion, 2 fluoride ion. The 1 in front of magnesium is not shown as is assumed to have 1. The 2 in front of fluoride is essential here. This concludes the video on Lewis dot structure. Hey everyone, if you found this video helpful, smash that like button and don't forget to subscribe. Want even more? Become a Patreon member for early access to videos, exclusive Discord discussions about questions on chemistry and physics, and live preparation sessions for your exams. Don't forget to head over to our website for topic tests and practice exams to further improve your understanding and learning.